The induction principle has to do with proving that some properties hold for all natural numbers n. So we are discussing about parametric properties, in other words, properties that are defined with respect to a parameter being natural number. So we will have something of the type p of n. And obviously p might hold for a number n, it might not hold for some other ones, but if p holds for number n, we sometimes say also that n has property p. So here is a very simple example. We would say, for example, in terms of the capacity of a room R, we can define that as a parametric property R of n. If you have an auditorium alpha with 150 seats, then obviously you will say that alpha of 150 holds, because that's exactly the number of seats in that room. But you would say that alpha of 50 and alpha of 200, it doesn't hold. You could also define the property in terms of how many people you can sit in that room, and then the property is going to hold for all natural numbers all the way to 150, but it will not hold for 151 or larger values. So here is how the induction principle looks like. I'm formulating this in terms of a lemma, and the objective of the lemma, or the conclusion of the lemma, is going to be that a property holds for all natural numbers n. And here is when this happens. You have this parametric property p of n that has two properties. On one hand, you have that p of 0 holds, so your property is true for the value of the parameter n equals 0. And on the other hand, you also have this implication being true. Whenever you have p of n holding for whatever value of the parameter n, if p of n holds for that value, then automatically also p of n plus 1 holds. So if your property has this property p of n satisfies the condition 1 and condition 2, then it holds for all natural numbers n. And we are going to apply this a lot, going into automata and thinking about successful computations and inputs that lead to successful or unsuccessful computations. And I want to prove this induction principle for you in this formulation. And the way we are going to prove it is going to use essentially the fact that the set of natural numbers is well ordered with respect to the usual less than or equal to order relation that we all know so well. So here is the proof of this lemma. I'm going to obviously deal with the property satisfying conditions 1 and condition 2, and I'm going to define set A to be all those natural numbers where my property P doesn't hold. And the aim obviously is going to be to show that A is empty. If it's empty, then it means that our property holds everywhere. But I'm going to assume the contrary and show you that I'm going to get to a contradiction. So I'm going to assume that A is non-empty, since n is well ordered, this implies that A has a least element. And this element is, let's say, k. Now we can think about this element k, and we can realize very quickly that k cannot be 0, simply because we have this condition 1 that says p of 0 holds. So because it holds, 0 cannot be an element of set A. A was collecting just numbers where the property doesn't hold. So k is not 0, and that allows me to think about k minus 1. So that's a natural number. And so if I think about k minus 1, you see k was the least element of A. And because it's the least and k minus 1 is smaller, then k minus 1 cannot be an element of A. And because it's not an element of A, what this means, simply by the way we have defined set A, it means that property P holds for k minus 1. Again, because set A was collecting only parameter values where the property doesn't hold. The fact that it's not in A, it means that P of k minus 1 holds. And now I'm looking at condition 2 that I know my property P satisfies, and it says whenever it holds for some parameter, then it also holds for the successor of that parameter. And we have that P of k minus 1 holds, so that implies right away by condition 2 that P of k holds. But if P of k holds, then by the definition of A, it means that k doesn't belong to A. And so we got a contradiction. On one hand, we have that k doesn't belong to A, but on the other hand, k is supposed to be an element of A, so that's a contradiction. And I'm going to usually show contradictions using this, this kind of broken arrow. And so, because it's a contradiction, it means that our assumption is false, so we say that A is in fact empty, and that establishes our property. A is empty, it means that there are no natural numbers where P wouldn't hold, and that's another way of saying that our property holds for all natural numbers, and that's exactly what the lemma was saying. So a few comments about this induction principle. It's a way to show that properties hold for all natural numbers, and to do that you essentially have to establish two things, these conditions 1 and 2. The condition 1 is also called the induction basis. So the first thing you want to do when you want to build a proof by induction is to show the induction basis, show that P of 0 holds for whatever property you want to show. And once you've done that, you've got to show the induction step. So this condition 2 is called the induction step. It's a step because, intuitively speaking, you make a step up from n to n plus 1. So what you do in this induction step is you are assuming that your property holds for some number n. You don't have to prove, you're just assuming that this holds for whatever number n, and using this assumption you are going to show that P of n plus 1 holds. This assumption P of n bears a name, and this is the induction hypothesis. So it's a hypothesis because you haven't proved, and you don't have to prove that P of n holds. You are assuming that's your hypothesis. If P of n holds, then you are going to show that P of n plus 1 holds. So we are going to discuss about all of these elements in any proof by induction we are going to do. First, we are going to establish the induction basis. You are going to show that P of 0 holds, and then you will say, now I'm working on my induction step. And in this induction step, you are going to have an induction hypothesis, and then you are going to have to prove this conclusion of the induction, namely that P of n plus 1 holds. So I want to show you an example how this is used in practice. And the example I want to show by induction is the following. I want to prove, so I want to say prove that the sum from I equals 0 to n by I is equal to n times n plus 1 over 2 for all natural numbers n. And obviously this equality can be proved in a number of ways independently of induction. In fact, there are maybe even simpler ways than using induction, but nevertheless I want to demonstrate induction on this particular property that this equality holds. So just to be in the framework of the induction principle, I need some parametric property. So I'm going to say property P. So I define property P, and this is a parametric property. I define the property P of n to be that this equality holds. So I don't know that this is true everywhere, but if there is a number n where this equality is satisfied, then I'm going to say my property P holds for that value n. And I'm going to show using induction that so I'm going to prove that P of n holds for all natural numbers n, and that's exactly the aim that we started with. It's just that now it's being rephrased in the framework of the induction. So we do induction, and to do this proof by induction, as I discussed, we have two steps. On one hand, we have to establish the induction basis. And in the induction basis, I have to think about P of 0. So P of 0, to have P of 0, it means that I have to calculate this sum from I equals 0 to 0. So remember, this was up to n, but now I'm thinking about n equals 0, so it's all the way up to 0. And it's summed by I. So obviously, there is, this is a trivial sum with no term, so that's 0. And obviously 0 can also be written as this, the result of this calculation, 0 times 0 plus 1 over 2, which is exactly what we were supposed to have in our property P of 0. So that means that P of 0 holds. And then once we've established the induction basis, then we do the induction step. And in the induction step, I'm going to assume, so I'm going to choose an n, or assume that the property holds for n, and so let n be one where P of n holds. So we have that I equals 0, sum from I equals 0 to n by I is equal to n times n plus 1 over 2. And I want to start working on my P of n plus 1 property, so that means that I'm just going to write it here. The sum applied to n plus 1 is about this, so the property for n plus 1 is about this sum, and this sum I can just write it down by taking to one side the first n, so the sum up to n, and writing separately the last term in this sum. And this now, and I'm going to write it here, this is true by the induction hypothesis. And the induction hypothesis was exactly this. I assumed that the sum all the way to n is exactly n times n plus 1 over 2. And that's exactly what I have in here. So by the induction hypothesis, I know that this sum is exactly n times n plus 1 over 2. So I'm writing here is equal by the induction hypothesis n times n plus 1 over 2 plus the last term n plus 1. And when I'm just doing the calculation, I can take n plus 1 as a common factor, and it's going to be n plus 1 times n plus 2. And if you check what we got is this, that we started with this sum all the way to n plus 1. So we started with the left hand side here applied to parameter n plus 1, and we got to this expression, which is exactly what we have on the right hand side when we are applying it for n plus 1. So that's going to be n plus 1 here and n plus 2 here, and that's exactly what we have on the right hand side. So in other words, what this means is that this implies that P of n plus 1 holds. So that's exactly what the induction step was aiming to do, assume that P of n holds and prove that P of n plus 1 holds, and that's exactly what we did. So by having established the induction basis and the induction step, we can now conclude by the induction principle that P of n holds for all natural numbers n, and that was exactly the aim that we had in this example. In some situations, you deal with properties that only hold for natural numbers from a certain threshold onwards. So you have such properties that are not true for some values of n, but then after a certain threshold, they hold everywhere. And you can also have a form of the induction principle that helps you establish such properties, being true after a certain threshold. And it's just a small reformulation of the induction principle, and its form is the following. I have it again in the form of a lemma, in the form of a mathematical result, and it says that if you have a parametric property P of n and a constant n0 greater than or equal to 0, such that you have these two conditions satisfied. On one hand, you have that P of n0 holds, and on the other hand, you have that whenever P of n holds, then also P of n plus 1 holds. So if your property satisfies these two conditions, then P of n holds for all n starting from n0. So this is very similar to what we had before. We have the induction basis here. And obviously, there is a small difference in here, that the induction basis is not talking about the property P of 0, but it's talking about a higher basis. It's talking about P of n0, whatever this n0 might be in your case. And we deal with the same idea of having an induction step. And this induction step is, in fact, of the exact same form as we had in the standard formulation of the induction principle. So we have this induction hypothesis, and you are assuming this induction hypothesis, and you are aiming to prove that this P of n plus 1 holds. So again, I want to prove this result for you, and I'm going to prove it using the standard formulation of the induction principle. And the way I do that is as follows. I'm going to define a property, so define a property S of n in the following way. I'm going to define S of n to be exactly equal to property P applied to n plus n0. So what this means is that whenever I talk about S of 0, in fact, I'm going to talk about P of n0. Whenever I talk about S of, say, 100, I'm going to talk about the property P applied to 100 plus n0 and so on. And so the aim is going to be to show that property S, defined in this way, holds for all natural numbers, which is exactly the framework of the standard formulation of the induction principle. And if I prove that S holds for all natural numbers, then obviously I'm going to get that P holds for all natural numbers greater than or equal to n0. So the aim is going to be to show that S holds everywhere. And we are going to do that by induction, using the standard formulation of the induction principle. And so we have to establish the induction basis. We have to show that S of 0 holds, but S of 0 is exactly, by definition, by the way we have defined S, is exactly P of n0, and P of n0 holds by condition 1 in our lemma. So this P of n0 holds. And then we have to do the induction step. And our induction hypothesis is going to be that we are assuming that S of n holds for some n greater than or equal to 0. and we are going to show that S of n plus 1 holds. Now, because S of n holds, this implies by definition, by the way we have defined S, that P of n plus n0 holds. And so this implies by condition 2 in our result that P of n plus n0 plus 1 holds. And so obviously this by definition implies that S of n plus 1 holds. Because S of n plus 1 is exactly the same as P of n plus n0 plus 1. So there you have it. The induction step is now proved. We assumed the induction hypothesis S of n holds, and we just proved that the S of n plus 1 also holds. So now we can apply induction principle. So induction on S shows that S of n holds for all natural numbers n. And this, as we discussed, means right away that P of n holds for all n greater than or equal to n0.